Okay, so our job is to find the derivative of this function I've called g, where that's the secant inverse of x. And just as an important notational point, you should always keep this in mind. Usually, when we put an exponent right there for these trigonometric functions, we usually mean you first apply sine of x, and then you square it. Okay, so that's, for example, what we would mean when we write sine squared of x. But here, that is not what I mean. Sine inverse of x is not the same thing as 1 over sine of x. You'll recall 1 over sine of x is called cosecant of x. Inverse sine is also called the arcsine of x. So there's a weird notation here. When we put a -1, that's not what we mean. But if we put any positive number here, this is what we mean. Alright, so sine inverse, just to remind you what the definition is, sine inverse is the inverse function. So this is like, remember, if you call a function f, then its inverse is often called f inverse. And you get the formula for this by taking y equals something involving x here, and then just kind of algebraically solving for x in terms of y and then swapping. So here you would write x equals f inverse of y. You just literally solve the formula. But the upshot is, what this means is when you have these two inverse functions, if you first apply f inverse to a value x, and then you apply f, it's as if you had done nothing at all to it. And the same is true vice versa. If you apply f first, and then you apply f inverse, it's as if you had done nothing to it. So that's what we mean when we talk about these inverse functions. So with that in mind, let's see how we can figure out what the derivative of secant inverse is. And the trick I'm about to show you works for any inverse trigonometric function. Alright, so the trick is you call another function, let's say f of x. Let's call that secant of x. And you consider the function f of g of x. And it's important that we put the weird inverse guy, the arc guy, on the inside. And we put the regular trigonometric function on the outside here. Well, since these are inverse functions, then this is just x. They cancel each other out. Now, take the derivative of both sides. Well, the derivative of the right-hand side is easy. The derivative of x is just 1. What about the derivative of f of g? Well, this is a composition of two functions, so we have to use the chain rule. So that's going to be f prime, we can do better, f prime of g of x times g prime of x. Now, g prime of x is the very thing that I was asked to calculate in the first place. So I can solve for it. G prime of x is equal to, right, I mean, they gave me g, secant inverse, and they asked me what is its derivative, so that's what I'm solving for. And it's just 1 over the derivative of f, but not applied to x, applied to g of x. Now, what is the derivative of secant? So the derivative of secant, you'll recall, and this is a good one to have memorized, it's just secant times tangent. And I want to be very clear about what that means. First you take the secant of x, then you take the tangent of x, and you multiply them. So that's what the derivative is. F prime of x is secant of x times tangent of x. So here, this is 1 over secant of, not x, because remember, we're plugging in g of x. Secant of g of x, or in other words, what is g of x? It's secant inverse. Secant of secant inverse of x times tan of x, which is tan of, again, not tan of x, sorry, tan of g of x. We're plugging in g of x. So that's tan of secant inverse of x, just like that. And you'll notice this simplifies a little bit. For example, the secant cancels with the inverse secant. And it's, again, for exactly the same reason, that's just x. So that's 1 over x times the tangent of the inverse secant of x. And for what it's worth, that is a technically correct answer. But you're probably not going to get full credit if that's what you leave your answer as. Because it turns out that if you first take the secant inverse of some number, and then you take its tangent, there's a much simpler way you could have gone through all of that without having to take the road of trigonometry. And in order to do this, you start by always drawing a triangle. You draw a right triangle, and you call one of those angles theta. And theta is supposed to equal, well, it's whatever that g of x is. It's always going to be g of x, where g is your original inverse inverse trigonometric function. For us, that's secant inverse of x. Okay, but apply secant to both sides of this. That's just saying secant of theta is equal to x. Right? You just, if y is f of x, apply f inverse to both sides. That means that x is f inverse of y. Right? That's all I'm talking about here. So x is equal to secant theta. Geometrically, what does that mean? Geometrically, secant is hypotenuse over adjacent, right? It's 1 over cosine. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. Well, okay, there's my hypotenuse. There's my adjacent. So if I call this x and I call this 1, and by the way, that's always what's going to happen. Right now, at this point, you fill in 2 spots of your triangle, okay? One of them might be the hypotenuse, one of them might be the adjacent, maybe the opposite side also comes up, depending on what it is. For us, it was secant, so it didn't come up. But one of them is always going to be 1, and the other is always going to be x. So you just let the numerator, wherever it is, call it x, and let the denominator call it 1. For us, the numerator was the hypotenuse, and the denominator was the adjacent side. So you call that x and you call that 1. But a squared plus b squared equals c squared, right? For a right triangle. That's the Pythagorean theorem. This side squared plus this side minus this side squared is therefore equal to this side squared. So actually, by Pythagorean theorem, this is the square root of the square of the hypotenuse minus the square of this side, which is 1 squared. But 1 squared is just 1, right? So you can check this out with the Pythagorean theorem. Okay, so now that we've filled in our triangle, let's go back. Tangent of sec inverse of x. Well, what is sec inverse of x? That is what I defined to be theta. So that's just tangent of theta. But what is tangent of theta? Look at your triangle. Tangent is opposite over adjacent. That means it's radical x squared minus 1 over 1. So what is this thing equal to? 1 over x times, and then tan of theta is just square root of x squared minus 1 divided by 1. Of course, dividing by 1 doesn't change anything, so that's really just 1 over x times the square root of x squared minus 1. And that's how you would want to play this game. So notice that this doesn't involve any nasty little trigonometric or certainly inverse trigonometric functions. So to be clear, since this is the sort of thing that you'll be called to do, perhaps, let's go through all of the steps here and let's highlight them. So the first thing we did is we composed the function we were interested in. We pre-composed it with the inverse function, the guy that's more normal. So if we're asked for secant inverse, we first applied that, then we applied secant, and we set it equal to x. So that was our first task, writing f of g of x equals x and choosing the right choice of f. If this was cos inverse at the beginning of the problem, you should have applied cos. If it was, cotangent inverse, you should have applied cotangent, and so forth. Then the next step is we took its derivative, the derivative of both sides of the equation, and we noticed the derivative of the right-hand side was 1. That's always going to happen. On the left-hand side, we used the chain rule and we wrote it like this. And then we realized, hey, wait a minute, that g prime of x is exactly what the problem was asking me for in the beginning. So let me just take 1 over f prime of g of x, and you just solve for it algebraically. And then you say, but wait, what is f prime of x? Let's just, for us, because we had secant as f, you figure out f prime was secant times tangent. But if f was something different, if it was cotangent or if it was sine or something else, then this would be something else. But you figure out what f prime is, and you figure out what g of x is, that's the thing you started with, and you write it all out nice and pretty. So you're tempted to stop here, okay? But you don't stop here because you won't get full credit. You want to draw this triangle. So what you do is you define theta to be your g of x. For us, that was secant inverse of x. And notice that that's always going to be what these aggravating little inverse trigonometric functions are in what you thought was your final answer. But it turns out it's not. So you always just define theta to be g of x. That always happens. And for us, that was sec inverse. Then you solve. Well, if theta is sec inverse of x, what does that mean for x? It means that it's secant of theta. Okay? And then you say, but what is secant of theta? So you draw your triangle now. Now's the time to draw the triangle and to call one of these angles theta. And then figure out, well, if secant of theta is x, then that means I can call whatever the numerator, which in this case was the hypotenuse because this is secant function, I call the numerator x. You always do that. And I call the denominator, which in this case was the adjacent side because, again, this is secant, you call that 1. You always do that. Numerator is always x, denominator is always 1. Okay, of course, the numerator and the denominator might change on this triangle, so you have to figure out what your function is. We were dealing with secant, so that's why it was hypotenuse over adjacent. If it was cotangent, then it would be adjacent over opposite, and this would be your x, and that would be your 1. So I hope that's clear. Then you use the Pythagorean theorem to figure out the third side. Alright, and so really think about it. I mean, it depends on whether you know the two legs and you're trying to figure out the hypotenuse, or you know the hypotenuse in one of the legs and you're trying to figure out the other leg. So don't just do this blindly. Actually apply Pythagorean theorem and think about it for 2 seconds. But once you have that, you just go back to the original answer that you thought was complete, but I just told you wasn't, and say, well, wait a minute now. Those aggravating inverse trigonometric functions are the very things I called theta. So here you're asked for secant of theta and tan of theta, and you can just look at the triangle and figure out what those things should be, and then you just replace them. And when you do, then you're done. You can maybe algebraically simplify if you want, but you're pretty much done at that point.